In this video, we will evaluate a line integral using the fundamental theorem. So first let's look at what this path is. The curve C says is the upper left quarter of a circle of radius 1 centered at 2, 0. So here's the point 2, 0. And here's a circle of radius 1 centered at 2, 0. And we're just looking at the upper left quarter. So from here to here. So just that. That's our path. And going counterclockwise, it says. So we're going from the point 2, 1 to the point 1, 0 along this circular arc. Now I said we're going to try to use the fundamental theorem, so we're not going to compute the integral directly. So the first thing we want to do is check if partial q partial x equals partial p partial y, where p and q are the components of f. So p is the x component and q is the y component. So let's see if this is true. So first, qx. So take the y component, which in this case is 2y minus x squared e to the minus y, and take the x derivative. So the first term doesn't have any x's in it, the derivative is just 0. And the second term, e to the minus y, is just a constant. So we're just differentiating x minus x squared. So we get minus 2x e to the minus y. Okay, now let's try partial p partial y. So we're taking the y derivative of the x component of f, which is 2x e to the minus y. So now 2x is a constant, and we're just differentiating e to the minus y. So the minus sign just comes down. And yes, they're the same. They're equal. So that means that f is conservative. Or path independent. In other words, it doesn't matter what path we take from the point 2, 1 to the point 1, 0. It's sort of irrelevant that we're told that we go along this circular arc. We can really take any path we like as long as it starts at 2, 1 and ends at 1, 0, and the answer will be the same. And furthermore, we don't even have to compute an integral, because we have the fundamental theorem. So a word of caution at this point: if at this point your answer were no to the first part and they didn't come out to be the same, then you cannot use the fundamental theorem, and the technique used in the rest of this video would not apply to the problem you're working on. But if the answer is yes, we can continue as we're going to. So, the fundamental theorem says that the integral along a curve of a conservative vector field, which means that it's the gradient of some function, is just equal to f at the endpoints, and you subtract. So if R is the parameterization for the curve C, and the parameterization goes from t equals a to t equals b, then you just plug in the endpoints into the function f and subtract. So there's something missing. We know these endpoints. For us, r of b is 1, 0, and r of a is 2, 1, the start and end points of our curve. But what we don't know is the function little f. We started out with a vector field, which we called capital F. So in order to finish this problem and use the fundamental theorem, we have to find this little f, which we call the potential function. In other words, we need to find the scalar function little f so that big F is its gradient. So this should be the same as the capital F vector field that we started with. So this is what we need to do now. We need to find the potential function little f with the property that its gradient is the vector field that we started with at the beginning. Okay. So remember what the gradient means. The gradient of a function is just its partial derivatives in a vector. So, if big F is going to be the gradient of little f, then P better be the x derivative of little f, and Q better be the y derivative of little f. So let's see what would need to happen there for that to be true. So let me repeat that. If this is going to be true, then what we need to happen is that the x derivative of little f should be the x component of the original vector field. So 2x e to the minus y. And from Calc 1, we know that if we have the derivative of a function and we want the original, we integrate. So f itself should be the integral of the derivative with respect to x. So, if we integrate this, the integral of 2x is x squared. And of course, whenever we integrate, we get plus a constant. But we only integrated with respect to x here. We pretended that y was a constant when we did this integral. So, when we write plus a constant, that's only a constant from the point of view of the variable x. It could be something that depends on y, so I'm going to call it g of y. So in other words, it doesn't depend on x. It's a constant as far as this integral was concerned, but it might have y's in it. Okay, now what do we do from here? We've only used half of the information. We have to somehow use q now, the y component of the original vector field. So this is what I'm going to do. I'm going to differentiate what we just got with respect to y. So we just took into account the information about x. Now we need to take into account the information about y. So let's take the derivative of what we just got with respect to y. So here we get minus x squared e to the minus y plus partial g partial y. Well, I guess I don't need the partial symbol since it only depends on one variable. So I'll write dg dy. So this equality, this expression here, came from differentiating our answer above with respect to y. But again, let's use the same logic we used before in the last step. If we want the gradient of little f to be the original big F, then we want this y derivative to be equal to what we called q at the beginning. So this needs to be equal to 2y minus x squared e to the minus y. So this needs to be equal to 2y minus x squared e to the minus y. And if you compare these two things, you'll see these terms are the same. So we can cancel them. And what does this tell us? This tells us that the derivative of g with respect to y is 2y. And so now integrate this equation. Now g is y squared. Again, plus a constant, but now it's a for real constant. Since we already took care of the x information, this is a constant that actually doesn't depend on any variables. And let's just assume the constant is 0. That's okay in these types of problems. Okay, so there's one more step. We now need to actually use the fundamental theorem. So go back to step 2 and plug everything in. Well, let's write our f once and for all first. So let's summarize all the information that we came up with in step 3. So put together what we found here and what we found here. So f is x squared e to the minus y plus y squared. Okay. Now let's go back and use the fundamental theorem. Since big F is the gradient of little f, the fundamental theorem tells us that it's little f of the endpoint, which, if we look back at our picture, was 1, 0. Minus f of the start point, which was 2, 1. So let's see, f of 1, 0. If x is 1 and y is 0, we get 1 squared times e to the 0, which is 1, plus 0 squared. So f of 1, 0 is just 1. And what's f of 2 comma 1? Let's see. If x is 2, then x squared is 4. E to the minus 1 is 1 over e, plus y squared, which is 1. And I should have parentheses around this whole thing, since that is all f of 2, 1. So the 1's cancel, and all we're left with is minus 4 over e, and that is our final answer.